There's been some wild news from the astronomy world about an interstellar object, 3I Atlas, that has dramatically changed color. This isn't a minor shift, it's significant enough to have astronomers buzzing and a bit concerned. Imagine your phone's notification LED suddenly switching from blue to flashing red for no reason. This event triggered alerts across NASA's deep space network, with multiple observatories reporting anomalous data. NASA has raised its alert status, coordinating a multi-telescope observation campaign. Initial reports suggest 3I Atlas might be becoming hostile, implying a rapid, energetic process unfolding millions of miles away. Our space telescopes, Hubble, Webb, Chandra and Spitzer, are now focused on this bizarre event. Let's break it down, telescope by telescope, and see what they found. First up is the Hubble Space Telescope, a marvel of human engineering and one of the most important scientific instruments ever launched into space. Since its deployment in 1990, Hubble has provided us with breathtaking images and invaluable data, revolutionizing our understanding of the cosmos. It's our reliable eye on the universe, orbiting high above Earth's atmosphere, free from the distortions and limitations that ground-based telescopes face. Hubble's unique vantage point allows it to capture the faintest glimmers of light from distant galaxies, nebulae, and, in this case, a mysterious interstellar visitor. When the comet known as 3I Atlas first entered our solar system, it appeared to be a typical interstellar comet. It reflected sunlight with a familiar bluish-white tint, much like other icy bodies that have passed through before. Its appearance was unremarkable at first glance, and astronomers expected it to behave much like its predecessors. Hubble's mission was clear: to measure the brightness and color of the comet over time, tracking any subtle changes as it journeyed closer to the sun. By monitoring these properties, scientists hoped to learn more about the comet's composition and origins. For several weeks, everything seemed routine. The comet's color and brightness remained steady, and the data matched expectations. But then, without warning, a sharp and almost instantaneous color shift occurred. The change was so sudden that it caught astronomers completely off guard. The comet's surface, once reflecting cool blue and white hues, began absorbing more of the bluer wavelengths and reflecting redder ones. This dramatic transformation made the comet appear deep red, a striking and unusual sight in the vastness of space. The data was solid and consistent, confirmed by Hubble's Wide Field Camera 3 across multiple filters. This wasn't a glitch or an artifact. The color shift was real and persistent, verified by repeated observations and careful analysis. Such a sudden change suggested that something significant was happening on the comet's surface. It could be a change in surface composition, perhaps due to the ejection of new material from the comet's nucleus, or some other process exposing fresh layers beneath the surface. The initial theory was that the sun's heat had exposed a layer of unusual reddish dust, causing the color shift. But as more data came in, it became clear that this was something different, something not seen before in any known comet. The red color didn't match any known compounds typically found on comets. It was unlike the organic-rich surfaces or iron-bearing minerals that usually give comets their color. This unfamiliar hue hinted at a new, possibly exotic material or process at work. The evidence pointed toward a process that was not passive. It could be a rapid chemical reaction triggered by solar heating, or perhaps a sudden outburst of energy from within the comet itself. Scientists debated whether this was a sign of volatile compounds reacting to sunlight or something even more dramatic. Hubble's visible light observations could only tell us what was happening to the light reflected from the comet, not the underlying physics driving the change. To truly understand the cause, astronomers needed more information, data from other wavelengths and instruments. Recognizing the urgency and significance of the discovery, the Hubble team quickly shared their data across NASA channels. This triggered a target of opportunity observation, a rare event that allows astronomers to rapidly redirect other telescopes to study an unexpected phenomenon. Soon, observatories around the world and in space were pointing their instruments at the comet, eager to capture every detail of this unfolding cosmic mystery. The astronomical community was abuzz with excitement and speculation. Meanwhile, Hubble continued its vigilant watch, monitoring the evolution of the red color and the changing shape of the comet's coma, the cloud of gas and dust surrounding its nucleus. Each new image and data set added another piece to the puzzle. But to truly understand the energy source and the chemistry behind this dramatic transformation, astronomers realized they needed a different kind of eye, one capable of peering deeper into the infrared and revealing secrets hidden from visible light. The scientific community turned to the James Webb Space Telescope, humanity's most advanced space observatory, for a deeper investigation. With its powerful infrared capabilities, Webb could analyze the comet's composition in unprecedented detail. The mystery of 3I Atlas's hostile turn was just beginning to unfold. As astronomers prepared for the next phase of observations, the world waited in anticipation, eager to learn what secrets this enigmatic visitor from beyond our solar system might reveal. When the Hubble Space Telescope first detected something unusual, it sent out an alert that set the astronomical community abuzz. Responding to this cosmic call, the James Webb Space Telescope was swiftly directed to observe the enigmatic comet known as I, Atlas. This marked the beginning of a remarkable investigation, leveraging the most advanced space observatories ever built. Unlike Hubble, which primarily sees invisible and ultraviolet light, Webb is designed to peer deep into the universe, using infrared light. This unique capability makes Webb the perfect tool for analyzing mysterious, color-changing comets, objects that often hide their secrets in wavelengths invisible to the human eye. With its massive gold-coated mirrors and cutting-edge instruments, Webb can detect faint heat signatures and subtle chemical fingerprints. Webb's near-infrared spectrograph, or NIR-SPEC, began collecting data. The results were astonishing. The instrument revealed the presence of superheated carbon monoxide gas and a variety of complex hydrocarbons, molecules that are rarely seen in such abundance on comets. These findings hinted at intense chemical activity taking place on or near the comet's surface. Even more surprising were the temperatures detected by Webb. The comet's surface and surrounding gas were far hotter than what would be expected from sunlight alone. This suggested that some other powerful energy source was at work, driving these extreme conditions. Webb's mid-infrared instrument, or MIRI, provided another crucial clue. It found that the dust surrounding the comet wasn't made of ordinary silicate rock, as is typical for many comets. Instead, it contained a significant amount of tholins, complex organic molecules that form under energetic conditions. Tholins are created when simple organic compounds like methane and ammonia are blasted with high-energy radiation or particles. This process not only explains the presence of these molecules, but also accounts for the comet's striking red color, as tholins tend to be reddish in appearance. In essence, the comet was acting like a miniature chemical factory, actively manufacturing complex molecules in real time. Laboratory simulations confirmed that such chemistry could occur under the extreme conditions detected by Webb. Webb's high-resolution images captured dramatic scenes, reddish material being ejected in powerful jets from specific regions on the comet's nucleus. These jets were not only visually stunning but also key to understanding the comet's rapid transformation. The sudden activation of these jets enveloped the comet in a thick, expanding red cloud. This phenomenon explained the rapid color change observed from Earth. Within days, the comet's appearance shifted dramatically, as it was shrouded in newly formed organic material. With these discoveries, astronomers realized the central mystery was no longer just about the comet's color. The real question became, what was providing the immense energy needed to drive these chemical reactions and heat the comet to such high temperatures? Detailed analysis showed that solar radiation alone simply wasn't enough to account for the observed temperatures and the energetic chemistry. Something else, something more powerful, had to be at play. To solve this puzzle, the scientific community turned to another space-based observatory, the Chandra X-ray Observatory. Chandra's ability to detect high-energy events would be crucial in uncovering the true source of the comet's mysterious energy. With Hubble and Webb's findings, the Chandra X-ray Observatory was called in. X-rays are signs of violent, high-energy events, not typical for comets. Initially, Chandra detected faint X-rays from solar wind interactions, but post-color change, it saw a dramatic flare-up. The comet was actively generating its own X-rays, a shocking discovery. The X-rays were hard, high-energy, and non-thermal, indicating particles accelerated to incredible speeds. The leading hypothesis is that the nucleus contains pockets of radioactive material. radioactive decay could generate heat and high-energy particles, explaining the observations. This process, known as Bremsstrahlung radiation, would produce the hard X-rays detected. The comet isn't just a chunk of ice and rock, it's a remnant of a violent, exotic environment. Chandra's data confirmed the energy source was internal and linked to the ejected material. The discovery of this internal X-ray generation solidified the hostile classification. The comet's environment is hazardous, creating intense heat and radiation. The final crucial piece of the cosmic puzzle comes from the Spitzer Space Telescope's extensive archival data, a treasure trove that allows us to peer into the comet's past with unprecedented clarity. Spitzer, with its sensitive infrared eyes, has been quietly observing the universe for years, capturing subtle changes invisible to other telescopes. Long before the comet's dramatic transformation, Spitzer observed 3I Atlas, providing us with a priceless before snapshot. These early observations are invaluable, offering a baseline to measure the comet's later, more explosive changes. The archival data revealed that the comet's dust was typical of what we expect from such icy wanderers, composed mainly of amorphous silicates and carbon grains. These materials are the building blocks of comets, formed in the cold, dark reaches of the early solar system. But when these before data were compared with the latest observations, the contrast was nothing short of staggering. The comet's dust had undergone a dramatic transformation, signaling a profound change in its internal environment. Spitzer's data showed a subtle but measurable rise in the temperature of the largest dust grains, a faint but telling precursor to the comet's later outburst. This warming trend hinted that something was stirring deep within the nucleus. This gentle heating suggested that the comet's internal engine, likely powered by volatile ices and trapped gases, might have been sputtering to life well before the dramatic events we witnessed. It's as if the comet was quietly preparing for its spectacular show. Spitzer's infrared spectrograph confirmed the presence of fluffy, amorphous dust, exactly what we expect from a cold, relatively inactive comet. These grains are fragile, unprocessed, and have not been exposed to significant heat. In stark contrast, the new dust released during the outburst was associated with red tholins and much higher temperatures, indicating a very different chemical and physical signature. This new material was more processed, altered by intense heat, and possibly by chemical reactions. The intense heat generated inside the comet would have annealed the dust grains, transforming them from their original amorphous state into crystalline forms. This process requires significant energy, far more than what sunlight alone could provide at such distances. Crystalline dust can only form at high temperatures, confirming that the heat source was deep within the comet's nucleus itself. This is a smoking gun, pointing directly to internal processes as the driver of the comet's transformation. In this way, Spitzer's archival data serves as the ultimate control group, providing irrefutable proof of the comet's dramatic and rapid change. Without this baseline, the true scale of the transformation would have remained hidden. The combined story told by all these telescopes is a masterclass in multi-wavelength astronomy. By weaving together data from across the electromagnetic spectrum, scientists have unlocked the secrets of a comet's hidden heart, revealing a tale of heat, dust, and cosmic change that would have been impossible to tell with any single instrument alone. 3I Atlas is an extraordinary interstellar object, a dynamic radioactive messenger. The discovery of an internal high-energy engine changes our understanding of these visitors. It suggests the universe can pack incredible surprises into small, icy bodies. The astronomical community is on edge, watching for changes in X-ray output and signs of fragmentation. This is a rare, real-time experiment in cosmic physics, and the story is still unfolding. We'll be following it every step of the way, breaking down the science as new data comes in. The universe constantly gives us new mysteries to solve, and this is one of the biggest. Thanks for watching, and stay tuned for more incredible discoveries from the final frontier.